I think we'll get started. And recording is now in progress. Okay, well, welcome everybody to the N3C Community Forum. So today we're going to hear from Tim Bergquist about the Pediatric COVID-19 BARDA sponsored data challenge, and very intriguing. So a challenge actually, as I just found out, was run from our very own Palantir Enclave. Next slide, please. So we're off next week for Juneteenth, and then 27th PPRL validation process by Sean Granis, and the monthly Recover COVID project team updates by Emily Pfaff. And then July 4th is July 4th. And then after that, we have a surprise presentation. I'm not sure what it is. And then the 18th is Kate Bradwell and Richard Moffat, the unit harmonization effort, which is appeared in print, very exciting. And those of us from a sort of lab background are very acutely aware that you think you've harmonized vocabulary, but if you don't deal with units, you get really weird results. And so Richard led I thought a really excellent study whose results I think are going to be used a bunch of places to sort of understand and develop methodology in that area. And then Nadia Safdar will talk about results from the vaccine effectiveness domain team. Next slide. So I think we're up to 1.5 million COVID positive cases, 14 million people records in the enclave. And on Tim to our feature presentation. So I think you could share your screen.
Do you see
the
screen?
Great.
Cool. All right. Well, my name is Tim Bergquist. I'm a research scientist at Sage Bionetworks, and starting, probably about 6-7 months ago, we started working on this pediatric COVID-19 data challenge, and I'm excited. And since then, it's wrapped up. We're now in kind of post-phase, post-challenge analysis. So I'm just excited to present the results of that challenge. So just quickly for the agenda, I'm going to be going over the challenge overview, what the tasks were, definitions, what data we used, and then the overall timeline. And then for those interested, I'll be talking about what the format of the submissions looked like, kind of how we evaluated them inside of the enclave, how we locked down data inside of the enclave, and then kind of the challenge judging process. What metrics did we use? What we looked at both qualitative and quantitative metrics. So how did we do that? And what that looked like. And then finally, I'll talk a little bit about the challenge winners and honorable mentions. I'll be touching on these each of these won't be a huge deep dive, so there will be some missing information, but hopefully there's something here for everyone to take away. So just as a quick caveat, this project has been supported in whole or in part with federal funds from the Department of Health and Human Services, the NIH, under grant number U24. You can read the rest of that. The findings and conclusions in this presentation have not been formally disseminated by the Department of Health and Human Services and should not be construed to represent any agency determination or policy. Sage Bionetworks was the contractor challenge administrator for the BARDA challenge as part of the NCATS collaboration with BARDA. And finally, the views and opinions expressed in this presentation are my own and do not necessarily represent the views of BARDA or any other agency. All right, so we hosted or I administered a pediatric COVID-19 data challenge. This was sponsored by the Biomedical Advanced Research and Development Authority, or BARDA. Think of them as DARPA for biomedicine and biological threat response. And they sponsored with the goal of eventually implementing the winning model for this challenge. Participants were competed for $200,000 that were split amongst, in this case, we did 2 winners. We originally were looking at 3. And then the winners we're eligible for follow-up funding that we are still exploring. So the two tasks that we started exploring, early on, we were discussing, we knew we wanted to do a pediatric challenge, and we gathered together some subject matter experts and were able to hone in to what we thought were two clinically relevant, possible to implement clinical questions that we wanted people to build predictive models for. So for task one, we asked of pediatric patients who test positive for COVID-19 in an outpatient setting, who is at risk for hospitalization? And then that task excluded same-day hospitalizations. So if you went to an outpatient setting and then went immediately into an inpatient setting, we excluded you from the evaluation. And then for task two, of pediatric patients who test positive for COVID-19 and are hospitalized, who is at risk of needing mechanical ventilation, cardiovascular interventions, ECMO, or who is at risk for death. We discussed a lot of different possible outcomes, and these were the ones that we came to where we decided that this is where the data met the actual outcomes, where the data was feasible to actually capture these, but also potentially be clinically implementable. Very quickly, our definitions were, we defined COVID-19 positive patients as patients who had a positive COVID-19 PCR test, not just a diagnosis. Hospitalizations for task one were defined as either an inpatient visit or emergency room visit. And then hospitalizations for task two were just an inpatient visit. Obviously, ventilation was just having a ventilation procedure code in the record. And then for cardiovascular support, we defined that as any of the following medications in some pre-built concept sets that TEL's team had developed. And those are the epinephrine, levo. I'm going to embarrass myself if I try and pronounce those, but vasopressors, etc. For the challenge data, so at the time when we locked down what we decided was going to be the training data for the challenge. So at that time we were kind of mid-July, and so we said the training data that was made available to participants was derived from the data from version 40 release, which was the N3C, all of the pediatric COVID positive patients as of July 30th, 2021 that were present in the N3C data set. And then over the course of the challenge, more and more data accumulated inside of the enclave. And then at the end of the challenge, we locked everyone out of their individual folders. And I'll talk a little bit more about how all that worked in a second. And then the testing data was pulled in as this prospectively collected data that represented version release, version 56, and was represented the pediatric cases in the enclave as of December 12th, 2021. So our training data set for task one, we ended up with 119,000 total COVID positive patients. 3,200 of them were hospitalized according to our previous definition. And then we considered them true negatives if they didn't have a hospitalization visit. And that was the rest of the 115,000. And then for the testing data, our total COVID positives were 144,000 patients. And then of those, 4,700 were hospitalized. So that was what we evaluated the models against. And we kept the training data the same, both when participants were building their models, as well as when we were evaluating. And then for task two, in total, we had of patients who had been for the training data set, 9,400 had COVID positives and were hospitalized. And then 815 had our outcome, 8,590 didn't. And then for the testing data set, a little over 500 more patients, so 9,000, almost 10,000 patients accumulated over the course of the challenge, and as being COVID positive and being hospitalized. And then that was shown as 708 outcomes in the testing data set. So fairly balanced. I think in general, you want a little less, you don't want it quite as equal, but that's just kind of how it panned out. So how much time we gave people? So for about a month, we had an onboarding phase, just due to the paperwork and red tape necessary to get involved in N3C. We tried to give people as much time as possible to get onboarded, get their IRBs in order. So we started our media push, our marketing in mid-August, trying to get people and tried to warn people, please get signed up as fast as you can or start the process as soon as you can, so we can get you on board as quickly as possible. So that was about a month of just trying to get people onboarded, get them some access to, I think we did some synthetic data that they could work with, just to kind of get familiar with the platform. And then on September 15th, we launched round 1, which was the task 1 question. We released into this space that I'll talk about in a second. We released all the COVID positive pediatric patients, as well as a training data sort of gold standard answer set that I had created while working with the subject matter experts as to what the true positive outcomes were according to our definition. So we gave them, we also had some tutorial materials in there for people to get some people oriented. There was a lot of new N3C participants. And then on October 12th, we started round 2, which is release the gold standard data for task 2, just to give people, and then a lot of people to start working with that data as well. And then on October 26th, we stopped the registration, so we didn't let anyone else in. And then we originally were going to stop rounds 1 and 2 on November 19th. And then we ended up extending that deadline for another month, just to give people a little more time. We got there's a lot of new users in this challenge. And so there was that initial, as people are familiar, there's a big learning curve early on when you're trying to work with N3C and the enclave. So giving people a little extra time once they kind of got caught up on that phase to actually start implementing some interesting results or interesting solutions to our questions. So that's the overall timeline. So now what we were having people submit. So people could either submit a code workbook, 1 per task, or they could submit a code repository. I think only 1 team ended up doing that, and they gave us a nice data lineage to work with, which I can talk about in a second. But most people submitted a code workbook. Inside of this code workbook, you needed to have your we had 2 sets of data that I made available to participants. So we had the training data. This represented all the 144,000 COVID positive pediatric cases. This was all the person table, measurement table, all the OMOP tables were available as the training data. And then we had a testing data set. While participants still had access to their code, I had created a dummy data set of testing data that was basically just 200 randomly sampled training patients that kind of held the place of this testing data. And so all teams had to do, or what we required teams to do, is to ingest these 2 data sets, do feature engineering, feature selection, model training, model testing, whatever it is you need to do inside of your code, ingest that data, and then all you had to do is output a file called task 1 or task 2 predictions that were patient level predictions for the outcome in question. So task 1 or task 2. So this is what this ended up looking like. This was an example I had created for people to begin working with. This is a very simple logistic regression that uses the pediatric, I think it's the pediatric complex chronic conditions with specific concept sets. So people could take this and then build out from there if they wanted to. So the way we made this work is inside of the Pediatric Severity Prediction Challenge DUR, RP 148569, there was a folder called Team Folders. And inside of that folders, each team had a folder that was given to them that was named after the team that they registered with. And I worked with Amin and Amin did a really great job of helping us set up the permissions inside of this specific work, inside of the specific project, so that I could actually assign read-only or view-only permissions to individual team members for their individual folder. And I can, if you want to ask questions, I can try and explain it more detail, but basically teams were able to access the resources folder, which is one of the folders at the high level inside of the project. And then inside of the teams folder, they only had access to their folder that they could do all their work in. So that way we were able to keep everyone somewhat separated. You were able to go into other teams' folders and read their file names, but you could not actually access any of the data or any of the code inside of any other team's folder. And so then at the end, once everyone, after the 2 months, after everyone had done other experiments and built other concept sets and done and everything, we expected teams to have a folder called output. And inside of that output folder, they had their task 1 workbook, their task 2 workbook, and then we required everyone to do a write-up for both their task 1 solution and their task 2 solution. And then in this case, for task 1, for team task 1 output, the workbook's just putting the output data sets into that folder. So that allowed me, it made my life a lot easier, and I didn't have to sift through, dozens upon dozens of files for every single team folder. I could just go directly to their output and ignore everything else. This is an example of one team's solution. This is kind of how complex it was, ended up getting, but on the top, it's kind of hard to read, but on the top here in the red, this was the training data that was coming in. And on the bottom here, this was the testing data that was coming in. So after December 17th, I was able to remove everyone's permissions from their individual team folder, as well as the resources folder and everything else in that project space. And then a little bit of background, so everyone in this project space didn't have access to actual N3C data. So normally when you get access to a project space, you're given a permission of either level 2 or level 3 data, and that dictates what you can access. The Palantir folks actually gave us custom permission labels that allowed us to lock everyone out from all the data. And then we had another project where I could curate the data and lock everything into version 42. I could remove all the adults, I could remove all the COVID negatives. And then I worked with Emily to transfer my new curated data set into the challenge project space that had our custom permission key or permission tag on that data. So then inside of this project space, all the participants had access to this specific data that I had locked in and curated for them. And so that was for the training data. So while they were building their models, they could use that data set. After we locked everyone else out on December 17th, I went back into our other project, re-pulled all the new prospectively collected data, removed all the redundant patients that were available in version 42, that were also available in version 56, and then pulled that new data set in to this project space. I kept the training data the same, but then I updated the testing data with this new prospectively collected data. If you're not familiar, when you work with a code workbook, you can actually run all the code logic in here with a tool that the Enclave provides called data lineage. It's actually, it's a really cool tool that I used a lot during this process. So you'll notice in the upper right-hand corner, you'll see a little branch symbol next to the main evaluation clean tag. What you can do is you can actually select all branches that are available among all data sets in this workflow. And so what I could, and if that branch doesn't exist for one of the data sets, you can set what branch it will default to. So in this case, I've selected the branch main evaluation clean. What that means is that the training data set will default to master, which is what we used originally, but the testing data set, which I updated, will then actually use the main evaluation clean branch. And then when you run all the code on those two data sets, it'll ingest the master, it'll ingest the other branch, and then it will create a new branch on every single one of those data sets that is being generated, so that you can track for every time you run this workflow on a new branch, new data is created on each of those branches. So I could run multiple experiments with, experimenting with different testing branches. The output prediction file would also follow that same exact branch, but the training data would stay exactly the same. So it's really a powerful tool versus manually going into every single one of these data sets, manually selecting the branch, etc. I could use this tool to just pick a branch, run it, and move on. That made my life a lot easier for doing that. So anyway, I think it's a cool tool. In addition to that code workbook, everyone had to submit a write-up describing their methods. We just created this template inside of the enclave. And so this was just using the reports tool. It's just the general like title, authors, what were your methods, what do you think sets your team apart, etc. And this was really key in helping us evaluate models, being able to dive into what their methods were. So after I ran everyone's models on the new data set, I was able to obviously generate metrics by comparing the predictions to our true positive outcomes. For our quantitative metrics, we use an F2 statistic, which is a derivative of F1 or also known as F beta. Basically, it puts a little extra weight on recall versus precision. We also use area under the precision recall curve and area under the receiver operator curve. And you can go on the Synapse landing page, but we combined all this with one big function into a single score. We also had a qualitative metrics section. So we didn't want to just find who's the most accurate model. We also wanted to look at which model, if we dive into different, we want to ask questions like, how does the model perform across different demographic groups? How does it perform across different timeframes? Can we actually interpret what the model is doing? And so we broke it down into two broad qualitative metrics, utility and reproducibility. So for utility, we looked at timeliness. Are the models accurate in a timely manner? Can we make predictions accurately well in advance of our true outcomes, or is everything that the model is accurately predicting within that first day window? Interpretability, do we actually understand what features are driving model performance, or is it just a big black box that we'll never understand? And then context utility, we looked at, I'll go into a little bit more about what that was, but we tried to break down, if we change the data around and look at different subpopulations, how do the models perform? And then reproducibility, how difficult is my life trying to rerun your model, basically. Prediction, is the model deterministic? I had problems in other challenges where we would run a model, it did well, and then rerun the model on the exact same data, and then it would just do poorly again. So we wanted to make sure that these were almost deterministic, if not, at least that they would be centered around, closely clustered around a single output or score. And then documentation, how good are your write-ups? How clear is the code? How good are the comments in each code? Is everything understandable about your model in your write-up and in your code? And we combined these in a way where we had people judging these individual metrics on a given scale, and then we took all the scores from all the different judges, turned that into a single score that was about 15% of the total score, and then the quantitative metrics are about 85% of the total score when we combine that into our single final model assessment. So the judging panel that looked at these models was made up of subject matter experts who had clinical, statistical, and informatics expertise. So we had clinicians, we had bioinformaticians, people familiar with N3C data, people familiar with clinical routines and how these might be implemented in a clinical setting. We had quite a range of people who were looking at these models. And then we put the models through a series of experiments looking at how different models performed across different clinical subgroups, demographic strata, longitudinal horizons, et cetera. So a lot of times what would happen is I would present as the findings of these experiments. I would then get requests to go back in and look at something else. I would do more experiments, come back a week later, present the findings. And just to kind of give you a flavor of what these looked like, here's something we looked at for judging all the different models that were at least relevant to us across different demographics, so racial groups. So we tried to see, do models perform differently across different racial groups? Do some fall off the map? Are there consistent patterns across all of them that would indicate that it's really a data problem, not a model problem? So what you're looking at is just the bootstrapped distribution of each of these models. I think it was N of 100, of how well they performed with using AOROC on each of these individual racial groups. The right bar chart is how large each of those samples are. So obviously white race is the largest group, with the smallest group being Asians. And we just, this was a small piece of what we looked at and looking and seeing like, okay, is there anything that is breaking, let's say in the top 5 models? they all look like they have fairly similar distributions, and then that would go into the judges' criteria for how they scored different things. We looked at timeliness, so how far out are models accurately able to predict, starting from, in this case, this is from week 1 to week 5. So if we look at only patients who have outcomes in week 1, how accurate are the models? If we only look at patients who have outcomes in week 2, how accurate, et cetera, et cetera. And there's some interesting trends you can see, like this, we had noticed this weird W shape that seemed to be an artifact of the data that we wanted to explore more. It's something I think we still have to do. And then we also looked at, sub outcomes. So obviously for task 2, we had 4 distinct outcomes that we were treating as one outcome, but we were curious to see if models were performing differently across these different outcomes. So we looked at mechanical ventilation, cardiovascular support, ECMO, and death across the different groups. Just to see if there was, if any models were standout in that scenario. And I am going quickly. There's a lot to digest. We spent a long time on each of these and just parsing through. So there's a lot more we could talk about here. And then finally, another example was we broke down the pediatric population into groups of patients who had at least one of the pediatric chronic conditions. We were trying to see if models perform better across different severity groups of patients. So for instance, the top category is neurological. So any pediatric patient that has a history of neurological conditions, we tried to see if those were uniquely accurate or less accurate across and compare those across different ones. We also had other ones where we looked at no comorbidities, etc. And then we also looked at, so when we pulled the new prospective data in, there was obviously new sites that weren't available in the training data. And so we broke it down just to see if we look at purely new external data sites, how well do models perform? They actually, a lot of them performed surprisingly well. They generalized pretty well to new incoming data sets. We thought that was very interesting. So at the end of this, 88 teams were onboarded into the N3C enclave. Of those, 55 models were submitted and evaluated against the prospective collected data. I think of those 88 teams, it represented around 250 people that were onboarded into the enclave. For task 1, the highest quantitatively scored model achieved an AUROC of 0.766. We knew going in that task 1 was going to be a difficult task, which is partly why we gave them 2 months to work on it. I think there is definitely room for improvement. We're undergoing discussions about what that'll look like after when we engage with the winning teams and what we might want to improve upon. And then for task 2, the highest quantitatively scored model achieved an AURC of 0.9. So we also thought that this one would be the easier one to achieve, and it's clear that when patients are hospitalized, there's a lot more data readily available, and I think it becomes more apparent who's actually at risk for those outcomes. I'm not going to be able to, I won't be able to take a deep dive into each individual model and looking at each individual, what their features were, but overall task 1, most models that were high performing used features like age, data partner ID, being able to control for which data partner the patient came from was actually an indicator of whether someone would be hospitalized or not. Whether a patient had a recent history of inpatient ER visit, what was their weight and BMI, and a lot of different measurements. But the top ones that seem to keep floating to the surface were calcium, creatinine, MCHC, urea, hemoglobin, hematocrit, and mean corpuscular volume. For those not familiar, hold on, I'm going to pull up my notes really quick. MCHC is also the mean corpuscular hemoglobin concentration. There was a lot of discussion about what that could be. It could be just that it's part of a lab panel that is just getting called whenever someone is severe in the clinic. It could also be a sign of anemia. And so there was a lot of discussion about what that actually might mean. For task 2, having a history of cardiovascular disease, extreme high and extreme low weight and BMI. body temperature, I can't remember if it was high or low body temperature, blood pressure, and volume of historical healthcare usage was used in most models. So for task 1, the winner was from the University of Wisconsin-Madison, the Department of Biostatistics, Professor Guan Ha, and his PhD student Ji Fan. Fun story, they were also the winner of a previous Dream Challenge using EHR data that I actually ran for the mortality prediction challenge. And then they were also I don't know if they won, but they were at least 2 or 3 for another COVID-19 data challenge that we ran at the University of Washington using their EHR. And so they've obviously learned a lot, and they have a great handle on how to build impactful models on EHR data. Just to go quickly into their methods. So for their feature engineering, they used what they called an ontology rollup. They mapped all the SNOMED codes in the enclave to either ICD-10 or to ATC, and then rolled up the ontologies to high-level concepts, which resulted in 288 mega concepts for conditions and 95 mega concepts for drugs, is what they call these mega concepts. They also, and so then for each of these high level terms, they also for each patient counted the number of times that those terms occurred within the records, both within 3 days ahead of the outpatient visit or just before, and then just to gather clinical history, they also looked at how many times do those terms occur before 3 days ahead of the outpatient visit. And there I kind of have a little graph showing that. The other big thing that really seemed to set them apart is the way they handled the data split. So they split their data by data partner, and they ordered the data by the number of COVID positives at each data partner. And then they took the top 64% of data with the most COVID positives and used that as their training data set, and then used the next 16% for tuning, and then use the final 20% for their own internal testing. And then in our analyses, it seemed that part of what happened is they generalized really well to new data sets as well as to future data that was incoming. This seemed the way they thought about this. It impressed a lot of people who were looking at this. And of course, since they were the winner of task 1, they ended up being awarded $100,000. So the key takeaway from UWMI, they accounted for COVID positivity across sites. Like I just mentioned, they were very careful with their feature engineering, but able to be ontology driven. But then also, I didn't mention this, for their measurements, they used a lot of concept sets to map obviously similar measurements into single vocabulary terms. So yay, data liaisons. All right, so for task 2, the winner was a company called Ver Biotechnology. They developed a missingness aware gradient boosted tree classifier. For their features, they use demographics, measurements, measurement of historical healthcare usage, that's number of records in the observation, measurement table, etc. And then they also created concept sets that were used. They also used concept sets to create 83 features. For their measurements, they included monocyte count, platelet count, BMI and body weight, creatinine levels, respiratory rates. For drugs, they included things like NSAIDs usage, hydrocortisone usage, epinephrine usage, and that was a history of usage. And then for each of those records, they bucketed it into 3 longitudinal windows. So for days 0 to 4 for the hospitalization index, for day 4 to 8 before hospitalization index, and anything prior to 8 days before hospitalization. They also looked at time to hospitalization from both the first and last record of each feature. So that X2 date of hospitalization, they would capture that time window for both the most recent and the furthest back feature record. So their final feature matrix included over 2,500 features. So a very large model, but paid dividends because they were very accurate in our quantitative analysis. We also did additional experiments to try and perturb the data, change things up to see how well different models broke down. And the model held up really, really well to new data scenarios that we gave them. So for key takeaways, 83 conditions, observations, and measurement features were derived from concept table. Those were each looked at with different in different time windows and for different time to hospitalizations. And then when we perturbed the data, the model held up really well to those data changes. Oh, sorry, I'm going to show this key takeaway. So on top of the winners, and they also were awarded $100,000 for the winning model for task 2. So in addition to the 2 winners, there were also 3 models that the judges and the evaluators all felt were deserving of honorable mention. The judges were extremely impressed with both their approaches as well as their quantitative metrics. So the first honorable mention for feature interpretability and design was OHSU. They used an ensemble classifier, but really what I think set them apart was they put a lot of thought into how their model would be used in the clinical setting. They seem to have take the spirit of the challenge in stride and even wrote additional sections in the write-up about how this model could be used for targeting monoclonal therapy. How can we reduce false positives, true positive, and they actually did some additional analysis on that front. Additionally, they had excellent feature presentation. So they visualized their feature, the Shapley values of their features, both on a population level, but also on an individual level. So for any given patient, you could go in and look at what Shapley value, what features were driving the prediction for an individual patient. So at the bottom here, we have a high-risk patient. This patient has a high MCA, high MALB, et cetera. And these, so you could actually visualize what is driving the prediction for the individual patient, but also looking at a high level for, in general, in the population, what are the highly predictive features that are driving their model. This was one of my favorite models. Personally, again, this is my opinion. This was my favorite models. I just really liked the visualizations. I really liked their code was really clean and easy to work with. So yeah, I think it's a very deserving honorable mention. Second honorable mention was for clinical utility. This was Bruce Craggan's model, and actually he was one of our resident citizen scientists that came in and had a very had a model with very good performance. But really, I think what I think the judges took away was that he actually had the smallest of all models with only 42 features, while still maintaining a fairly high quantitative score. This is important because what we kept running into looking at different models was that some of them are just very, very large. And so when you're trying to think about how we could implement a clinical model, obviously the larger the model, the more you have to map into a live EHR clinical setting. And so this idea that this model would be the easiest to implement because it only had 42 features, I think really resonated with us. And also each feature could be included in a clinical implementation. So not only were the features, were there a small set of features, but each feature was mappable and readily available in a live clinical scenario as we looked through them. So yeah, shout out to Bruce. He did a fantastic job. And I think this just goes to show the cool collaborative nature of N3C, where we can bring in citizen scientists and they can contribute in really positive ways. And finally, we have an honorable mention for computational methods. This was from Joy Amalgir from RE Science. They built a ensemble model where each of the ensembles in the ensemble was a clinically relevant prediction question. So there were things like a model built only on COVID data prior to COVID. I think it was a model built only on data of same day of hospitalization or same day of outpatient visit. And then there was other ones like an ensemble model, a model built only on a pediatric cohort, et cetera. So most teams were using XGBoost, which, if you're not familiar, is just an ensemble model where it builds. It's not a random forest, but it builds these. I can't remember the exact terms at the moment, but it is an ensemble of ensembles. But each individual ensemble is not designed. In this case, they specifically designed each of their ensembles in a very intelligent way, and it was the most interesting computational approach of the challenge. So lessons learned. So I think we used F2, AUPR, and AUROC in our quantitative metrics. I think it would have been good to have some sort of calibration metric in there, whether it was calibration error or Breyer score. We did look at calibration as in our qualitative assessment when we looked at clinical utility. But I think going forward, I would want to have some sort of calibration measure included in our quantitative metrics. We also started finding that the prioritization of quantitative accuracy led teams to build models with less clinical utility. So in order to try and maximize their quantitative accuracy, teams were grabbing as many features as humanly possible in order to squeeze every little bit of accuracy they could, rather than being really thoughtful or selective about their feature engineering and selection. So I think at least for these types of challenges, and when we're evaluating models for possible clinical implementation, it may be worth thinking about how we can balance the incentives to get people to think more carefully about their features, while also trying not to sacrifice too much accuracy at the end of the day. And another big takeaway was the winners were not only the top performers for quantitative metrics, but also had really high scoring qualitative metrics as well. I think the key takeaway is really good design leads to really good, accurate models. So I don't think forcing people to think carefully about their features is going to result in less accurate models. That's just kind of what we found. So just to thank the institutions and researchers involved, obviously Sage Bionetworks, I was the challenge administrator. Richard Moffat and Tel Bennett were both administrators, as well as part of the design the design of the challenge questions and the challenge in general, as well as support throughout the challenge. The sponsoring organization was BARDA, Biomedical Advanced Research and Development Authority, and this was in partnership with NCATS, NICHD, or the Eunice Kennedy Shriver National Institute of Child Health and Human Development, as well as Health and Health Resources and Services Administration. I would also like to thank the N3C community. This wouldn't be possible without this incredible resource, and I didn't have to think about governance that much because all that work had already been done, all the groundwork had been laid for that. And really also a special thanks to the Palantir team, who I know went above and beyond to make this happen. This was a great challenge, I think, because it caused a huge surge of new people to come in, because we were pulling in people who hadn't heard of N3C before. That also meant SOD had to do a lot more tutorial sessions and a lot of debugging with issues for them. And yeah, just thanks to Amin and Emily as well, and Kate for all their work in helping me design the project space, get the data onboarded and everything. So anyway, that is my presentation, and I will take any questions.
Thanks. Great talk. So I'll start out with one question. So these seem like really interesting and obviously should be quite generalizable, as in part you've tested many types of generalizability. And maybe you said this already, but are these models available on the Knowledge Store or otherwise publicly accessible?
They are currently still in the pediatric severity prediction project. They are not yet available. That's something I think we'll explore, and I think that will also be up to the individual teams about whether they want to post those as templates or as knowledge objects. That I think that most likely be left up to the teams.
Okay, yeah. Now that'll be very interesting. And was there interest or did any groups try to do something more in a sort of deep learning, less feature engineered way?
Yes. So I believe there were teams that were using GPUs. We had a lot of issues with those. I think the GPU environments at the time weren't super stable. So when we were trying to rerun everything, we had a lot of issues with those. Yeah, that was Amin and the Palantir folks had to. I think that ended up going a few levels to actually fix a few issues. So I think there was still some bugs to fix out there. None of the top models were deep learning or neural networks. I think partly because they didn't want to run too long. And so they were worried that if I had to rerun everything and it was taking 10 hours, that we wouldn't run all the way through. So most models ended up taking, I think there were some quick ones that were like an hour and then some that were 4 to 6. And I think a lot of people just went with XGBoost just because it's a little faster. So yeah, it's hard to say what would have allowed people to do more with their with neural networks. I think some people did. I just don't know if the GPU system profile was quite ready at the time.
Great. And Anjali Sharath Kumar asks, if I understand correctly, the model was validated with real data. Why awards were not given to 4 teams instead of 2 teams? Funding helps.
What do you mean real data? Like if you're assuming, I mean, N3C is real data, I guess. So are you saying like what if it was validated on like on-site data?
I don't understand this myself. I'm actually just
Okay.
reading the chat, to be honest. It does.
So the models were validated on incoming data from that it was already going to be an N3C. So we were just trying to make sure that we're trying to limit the ways people could cheat. The one way we could do that is to lock in data on a specific version, then bring in a new version later and validate the models on those. As to why 2 teams were awarded, not 4, real data versus synthetic, yeah, it's real data. So why it was 2 and not 4, that was BARDA's decision, and I can't speak for BARDA's decision-making process.
Great. Okay. And and it was validated on a different time slice of data.
Yeah.
Which actually does raise some interesting questions of changes in the variant and in treatment. And I suppose it would really be variant given what you were doing.
Yeah.
But you can't control for everything.
Yeah. There is a question from Manuela. When will the teams find out how well or badly they did, and when will they get access to the team space? So right now you can actually access your code. Later this week, we're going to be you'll have access to the training data as well as the validation data that we use to test models. So you'll be able to generate your own scores. The gold standard scripts are the same ones that I made available in the resources folder. So you'll be able to regenerate all those. At this point in time, we're not going to be releasing a comparison or like a leaderboard for all the different teams. That's at this point in time, that's just, we're not going to do that. But you'll be able to generate your own score and see how your model did on the new data.
Excellent. So, all right, and thank you. Well, this is really fantastic. Any last questions? Okay, I think okay, yes. Okay, so we have Lauren Walker with relatively low morbidity, mortality numbers in kids. Is there thought of applying this methodology to other infections like influenza?
When you say methodology, do you mean a community challenge or specifically the models that were developed?
Good question. Both. Let's try it both ways.
Okay. I haven't given a ton of thought. I mean, I'm always open to building more community challenges around that type of data. At this point, I don't think N3C would be able to do. We wouldn't have. I don't know how good the data for influenza would be inside of N3C. Yeah, I guess to answer your question, I haven't really thought about it, but I think it'd be interesting.
It would seem like the certainly from a methodology point of view, one could do things in a very similar way. Obviously, you'd need a different enclave or a different charter for the enclave because the data being gathered isn't influenza centric, and the charter and funding and general IRB permissions are COVID specific. But so I think it would sort of have to be more of a methodology. But I do think that and I think there's your methodology of evaluating this stuff and what you're asking for is a little different, substantially different than a lot of challenges, which is interesting.
Yeah, and just a side note, Marie Wax is in the chat. She was she's the contractor for BARDA that was the administrator of the challenge, or not the administrator, the lead of the challenge. So I see you answering some questions there. Thank you, Marie.
Okay, we'll get in touch with the winners for the collaboration phase. And then Meena Mishra, when does the collaboration phase start and what would it look like?
Yeah, well, that's we are in the process of staking out what exactly that will look like.
Yeah.
And you're welcome, Meena. I really did like your method. Yeah.
Wonderful. All right. Well, thank you. This was really interesting, and lots of us, I think, were really eager to see what came of this. So it was very, very interesting, and we'll look forward to this as the next phase evolves. Okay.
Yeah.
Thanks for talking. This was great.
Yeah. Thank you. And if anyone has any questions, feel free to email me or shoot me a present or shoot me something on Slack.
Okay. Thanks, everyone. Bye-bye.